Okay, thank you everybody for coming. My name is Nicholas Clinton, Earth Engine Developer Relations. I'm here to talk to you about the Forest Data Partnership. And this is the link to this slide deck in case anybody wants it. You can get FODAPA_AGU and you'll have all these slides. So, the Forest Data Partnership is a collective approach for ending deforestation and accelerating restoration. And the idea is that there are a lot of maps out in the world of all kinds of things that are relevant to commodity supply chains. And when these large companies have commitments to ensure that their supply chains are deforestation free, they need geospatial data so that they can live up to those commitments. But there are lots and lots of maps. And which one do you believe? That's the first question. The second question is, do you make another map, or do you use an existing map? And this is a challenge in private industry and conservation because it sets up a competitive environment. Everybody has different maps of the same commodity. Nobody knows which one to believe. Everybody would like to claim that their map is the best. And that creates a lot of confusion among the companies that want to capitalize on this data in order to live up to their commitments. So that's the purpose of the Forest Data Partnership, is to have a collective approach to solving this problem. So we want to create source of truth maps or harmonized maps that are not throwing away any existing information, but helping companies to understand which ones to simplify their choices in this matter. So these are the founding partners. This is a 5-year project funded by USAID, and we have both public and private sector players in this partnership, but we're welcoming more participants. So if you are a data producer or a data consumer, we would love to hear from you. So please do check out that website, forestdatapartnership.org. There's a form at the bottom that you can fill out if you'd like to get involved. Okay, how's it going to work? We've got 5 sort of work streams, if you will, and these are more or less synchronous. So the idea is that first you want to engage with the relevant players. So if there are large companies that are consuming geospatial information, if there are large producers of geospatial information, we want to engage with those folks in order to ensure that they are part of this process. The second question is of alignment. So there could be lots of different companies who are all asking for similar kinds of data, but maybe not exactly the same. So the second part of the process is getting these players aligned into what they really need and whether we can produce one source of truth data set that will meet the needs of multiple consumers of the data. The next part is innovation. So we're going to have to either harmonize or create data sets de novo in order to meet the demand. And then we deploy it. So if you're a company and you want geospatial data, you want to just get it from somewhere easily. You don't want to have to write a bunch of code to get your data sets. You want to just be able to connect to a system. And that's the deployment phase. We hope to be hosting data products on Google Cloud Platform, for example. And then we want to assess our impact. So we're not just doing this for fun. It is fun, but that's not the only reason. We want there to be actual change on the ground. So reducing deforestation and increasing restoration using geospatial data. Okay, this is a demand-driven approach. So here we have cocoa and palm and timber, and these are, all of us are demanding these products. We're using, I ate some chocolate the other day. I used some soap this morning that probably had palm oil in it, and I slept in a bed that was made out of wood. So we're all consuming these products, And that's the idea, is that, that consumption is not going to stop anytime soon. So we want to ensure that the producers of these products are able to get the information that they need to ensure that the products are deforestation free, or are making the best use of the natural resources. So that's what we mean by a demand-driven approach. We're focusing on commodities here that are actually causing changes on the landscape on a daily basis. Okay, how does it work? This sort of cartoonish diagram is intended to represent the traditional way of developing geospatial data sets. So we have some, for example, this is a plantation, and we'd like to know, where these plantations are and how old they are, and so on and so forth. We can't necessarily do that without field information. So that's the idea here, is that we're sort of enabling users on the ground to create field information. We are creating information that we can see online, feeding that into a cloud-based machine learning platform, such as Google AI platform or Vertex AI. And we're also feeding in geospatial data. So lots of imagery, spectral indices, radar data, that kind of thing is also being fed into this platform, which spits out a map to the user. In this case, the user is a consumer of this information. And as you can see, the user is very happy about their map, and that helps them to improve their sustainability, and everybody lives happily ever after. This is sort of the traditional approach to creating these data sets, but we don't want to get in competition with the data sets that already exist. We don't want to just create another palm map or another cocoa map or another forest map. We'd like to make use of the maps that are already in existence. And that is a harmonization process. So the idea of this is that there are lots of players in academia and industry who are creating maps. And which one do you believe? It's very hard to tell, and this opens the consumers of these products to criticism. Because if somebody says, well, I'm using map X, and then the next player says, well, I'm using map Y, I believe map Y is better, and therefore, if you're using map X, you're not really living up to your commitments. We'd like to avoid that sort of controversy by harmonizing the existing maps. And that's the idea here. You put the existing maps into an ensemble. You collect some raw data. And the reason this is sort of partitioned in this way into private and aligned partners and public is because some of these data are very sensitive. So, for example, the location of smallholder cocoa farms could be subject to government harassment in the event that their information becomes public. So we do need to be very careful about keeping this kind of sensitive data private. However, we can anonymize it through processes of aggregation, for example, and we'd like to use anonymized or safe data to train the ensemble, and I'll explain exactly what I mean by that in a second. But the idea here is that we take existing maps, we take raw data, we sort of build this process inside a clean room where the data is not going to leak out. These might be proprietary maps; those aren't going to leak out either. And once we've harmonized this stuff, we can release it all to the public. So everything that we do is intended to be open source and available to the public. That includes both the harmonized maps of the important commodity and also the uncertainty, but also the reference data. We're going to make all this stuff public. Questions before I move on? Yes.
Are you considering the conversion of other land cover, other ecosystems outside of forests driven by commodities?
The question is, are you considering other ecosystem types besides forests? And the answer is yes, but we are trying to maintain our focus on forests in order to avoid getting spread too thin. So we are planning to focus on forests, but what that means is that if there are areas that have been deforested, those are also relevant to this project, even if they've been converted to another land cover in the interim. Other questions? Okay. In the top row here are 3 palm oil maps. Which one do you believe? I'll give you a hint. Don't guess. There is a way to combine these using more geospatial information, specifically more training data. And that process is called meta-learning. In fact, it goes by many names, but one name is meta-learning. Please see Wolpert 1992, Stacked Generalization for more information about this approach. I believe this is the seminal paper. There might be earlier ones, but certainly that's a very influential paper. The idea here is that by combining 3 disparate data sets with more training data, you can create a harmonized product that is optimal in the sense of higher accuracy than any of the individual maps in the ensemble. Let me say that again. If you generate a new data set, a reference data set that has not been used in training of any of the existing data sets, you can assess the accuracy of any of these data sets. And if you do the meta-learning correctly, the harmonized product will be higher accuracy than any of the individual maps in the ensemble. So that's the promise of this approach. And it does take more training data. And that's a big component of the Forest Data Platform, Forest Data Partnership, is obtaining these the training data that we need to harmonize these products and create new products or validate existing products. So here's an example of this. This is an area near Kuala Lumpur of palm and agriculture and mixed land use here. And the points that you see here have been labeled by at least 2 observers. And it's a very simple labeling project. It's either palm or it's not palm. And so if it's palm, that's a yes. If it's not palm, that's a no. And if the two or more observers disagree, then it's a maybe. But we can still estimate the probability from the human observers here, and that's the idea. Is that it's kind of hard to tell in the slide here, but the different colors in the background are different maps, and they're in disagreement, and we don't know which one to use, which one's better. The idea is that we can combine them by using more training data, and that's what these points are for. So, for example, the points are overlaid on the 3 products in the top, and a machine learning predictor is trained, and what you get out is the map on the bottom, which is an optimal combination of the 3 inputs. So that's the idea of collecting more training data here. Okay, just some background on how this process works. We have a base learner, capital G for generalization. It's taking Z, a vector of geospatial inputs, and it's guessing G, which is the prediction of V, the value that you really care about. Maybe that's palm, maybe that's cocoa, or some other thing. Z is just the inputs, vector of covariance at that location. So here's the ensemble. We've got all these generalizers or all these learners. These are the base predictors in the ensemble, and each one of these is different. So it might take a different vector of inputs, and it hopefully produces a different output. The effectiveness of this approach, in fact, depends on the diversity of these predictions. If they're all making the same prediction everywhere, this is not going to work. So you need base classifiers that are strong in sort of different parts of the feature space or different parts of the geographic problem space that you're concerned about. Okay, at location XY, you have the true value. And you also know the index of the base model that is closest to the true value. And this is sort of the basis of meta prediction, is that you're going to stack all this stuff together. So this bolded G is a vector of the guesses of the models in the ensemble. M is the meta learner, and that can predict a couple things. It can predict either the palm value directly, or the commodity value directly, or it can predict the label of the base learner that is most accurate at that location. So the important point to get about all this notation is that there's a set of classifiers here that are strong in different areas. So one classifier might be good over here, other classifier is good over there. We would like to predict at any pixel which classifier is going to be the best, and that will vary. So the idea is that we're capitalizing on the strengths of each model in the areas where they are most effective. And that's the basis of meta prediction, and that's what we're doing here. We're either predicting the label or we're either predicting the value or the label of the best model, and then we output the result. So that's sort of the formula here. Let me just get all this stuff. Okay. How do we do it? What we really need is more training data. And the gold standard is ground data. That is important for a couple reasons, and let me explain why. First of all, the people that live in those locations are the most qualified to observe what's there. Not one of us sitting in an office, with the heater on and a high-res image, and we think we know it's there, but we're not really sure. And it's the folks on the ground that are really experts there, and they can tell you what the true label is. Furthermore, let's say that you produce a model with some data set that predicts in somebody's yard, whether it's palm or cocoa or corn or some other thing, but the model's wrong. That person should have the opportunity to correct the record. If the model is wrong about what is happening in their backyard, those people should have recourse. And what we're hoping to do for those people is set up a platform, a mobile platform that will enable them to contribute data to the training data set that we're using to do the harmonization. So we actually have an open source project at Google called Ground, which is being led by one of my colleagues, Gina Maselli. And the Forest Data Partnership is going to be leveraging Ground in order to give anybody who has a stake in this mapping the ability to contribute either training or validation data to the harmonization of the map products that will be used by commodity producers to meet their commitments. So the idea here is that we're not just doing satellite interpretation, we're also setting up a mobile platform that will let any user anywhere in the world contribute information to the system. So that's the idea. How did I do on time? Not too bad. Please do contact us to get involved. If you want to go to that website, you can learn a lot more about what we're doing. As I say, there's a form at the end. If you're a data producer, we'd like to hear from you. If you're a data consumer, we'd like to hear from you. If you have any ideas about how to make this work, we'd be very interested in hearing from you. So please check out the website for more information. Thank you very much, and I'm happy to take questions. The question is, how do you use which model to use for the right pixel? These are the predictions in the pixel. And what we know at that location is the true value. So we know that one of these is closer than the others to the true value, but we also know the other guesses. We stack these guesses into a vector, we feed those into this other learning algorithm. Let's say M is just random forest here. So we feed this vector of guesses into M, and M is trained by the right answer. So M is trained by V here. M is trained to predict V from the individual guesses. An analogy here is like a committee of experts. So each of these individual elements of the ensemble is an expert, and they're all making guesses. But the committee has to have a chairman who decides which of the experts to believe. And that's the role of this meta learner, is to aggregate these guesses in a way that produces the optimal value in a given pixel. Those guesses are going to be different in each pixel, and so you can predict which one is right. But you can also feed this vector of covariates to the meta learner here. So not only does the meta learner have all the guesses, it has the feature space that the individual based classifiers have used too. So for example, you feed it all the guesses and then you feed it spectral information as well, so that the learner can learn which of the individual experts in the committee knows what it's talking about at different parts of the feature space. That's the basic idea here. So the question is, are we looking at the temporal aspects? Absolutely. So when you collect the reference data, you're making a prediction at the time of that reference data. Even if these guesses were from years ago, that still is predictive of what's going on right now. So the idea is that the temporal component is determined entirely from the training data, and but once this is set and these guesses are made, then you can play that backwards and forwards in order to get change over time. So yes, that is absolutely part of the process here. Yeah. Okay. So the question is, what kind of uncertainty are we getting here? And the idea is that this is a pixel-wise uncertainty. So, for example, you might have this set of maps in the ensemble, all of which are have some global accuracy number. But even if those accuracy numbers are exactly the same, the accuracy differs spatially. And the goal of the meta learner is to predict which one is best in which location. So yes, we will have pixel-wise uncertainty in addition to a global number.